Welcome to the exercises for chapter 14. Amazing that you got this far. You should pat yourself on the back, buy yourself some ice cream or a piece of chocolate, however you like to reward yourself, and then let's get back to work. So here is the video for exercise 1. So the idea is we're going to explore symmetric matrices, so square symmetric matrices, and the relationship between the singular values and the eigenvalues. Now, the relationship between eigendecomposition and singular value decomposition is a little bit nuanced because there are certain types of matrices where eigendecomposition and the SVD are really, really similar to each other. In some cases, they can be identical to each other. But eigendecomposition and singular value decomposition are different. They give different results for different kinds of matrices. For example, non-symmetric matrices. Obviously, if your matrix is rectangular, if it's non-square, then eigendecomposition doesn't even exist. Okay, but you learned in this chapter that there is a very special relationship between the SVD and the eigendecomposition of a square symmetric matrix. And that is your goal here, to explore this relationship. So create a 5 by 5 symmetric matrix as A transpose times A. So a matrix of, 5 by 5 matrix, and you want to make sure that this is obtained through the multiplicative method of creating symmetric matrices. So A transpose A. Of course, you can also do A times A transpose. That doesn't actually matter for this exercise. Okay, so then what you want to do with this matrix is eigendecompose it and singular value decompose it. And then compare the right and the left singular vectors and also the eigen vectors and the singular vectors and the eigenvalues and the singular values. I'm getting confused between all these terms here. Okay, so I hope that makes sense. Basically, we're comparing the output of SVD and Eig for a 5 by 5 symmetric matrix created through the multiplicative method. Next, once you have done that, I want you to repeat it for the additive method for creating a symmetric matrix. So remember that A transpose plus A will also give you a square symmetric matrix, assuming that A is square. Now, this method of creating a symmetric matrix and this method have some properties in common. For example, both are guaranteed to produce symmetric square matrices, but they do not share all of their properties in common. And, well, that is what you are going to discover and think about in this exercise. Okay, so now I will switch to Python and walk through the code for this exercise. I start off by creating a 5 by 5 random matrix, and then I make it symmetric by A transpose times A. Here I have A plus A transpose. I don't know why I did the transpose in the second matrix and on the first, but that actually doesn't matter. But we're gonna get back to this later. Okay, so here we take the eigendecomposition, and here we take the SVD. And now it turns out that comparing these is going to be sort of complicated or much easier depending on whether the eigenvalues and the singular values are sorted in the same way. So what we want to do here is sort the eigenvalues descending. So that's what I do here. And then also you want to sort, of course, the eigenvectors. You know from previous chapter that you cannot sort the eigenvalues without sorting the eigenvectors. You really have to, they're inextricably paired. So whatever you do to one, you have to do to the other. And you also learned in the previous chapter that you cannot, or you have to watch out for easy to make coding error where you're sorting like this. So here we are sorting the rows, not the columns, which means we are totally, completely screwing up the eigenvectors without actually making like a real coding error, right? Python is not going to crash. I'm running this code just to show that Python doesn't produce an error or a warning message here. Okay, so you have to be mindful of that. So let's see, here we have the SVD. And then I'm comparing them. So I'm just going to put them into two columns of a matrix, the eigenvalues and the singular values. And let's already start inspecting these. So just pay attention to this for a moment. Here you see the eigenvalues of A transpose A. and the singular values of A transpose A, and they're exactly the same. Here you see the right and the left singular vectors subtracted, so that's here. The uh, left singular vectors versus the right singular vectors. Now, remember, is another potential source of confusion with the SVD. Remember that what Python is actually returning here is not the matrix V, it is the matrix V transpose. So if you want to compare U with V, you actually need to transpose this matrix because you're effectively transposing it back to be V, where the columns contain the right singular vectors. Okay, and then we can see the special property of the SVD of a symmetric matrix defined from A transpose A, which is that the left and the right singular vectors are identical to each other. So we subtract them and we get the same thing. Now, what does this mean? This in combination with this. This means that the eigenvalues are the same as the singular values, and the left and the right singular vectors are the same as each other. And that in turn means that each of these matrices, so the singular vectors matrices, is identical to the eigenvectors matrix. Now, that is true. First of all, that's true only for this very special case where we have the matrix A as being defined by a matrix times its transpose. Okay, and then, so it's also only true up to a potential sign reversal, right? Because eigendecomposition has this fundamental sign indeterminacy included. So therefore, to compare the left singular vectors with the eigenvectors, I actually run this twice. So I say U minus the eigenvectors and U plus the eigenvectors. And what we should find is that basically all of these are zero at least once. So run this again, we're going to find different columns that end up being zeros. That's just related to the uncertainty. Another way you could have done this is by taking the absolute value of the correlation coefficients between each vector, so each column of U and each column of V or evex. And there you would see that the absolute value of those correlations should be, basically 1 plus some rounding errors, maybe 0.999, something like that. Okay, so that is for A transpose A. And now what I'm going to do is comment this line and uncomment this line. And the question is whether this observation, this relationship between the eigenvectors and the singular vectors also holds true for any symmetric matrix, regardless of how it was created. And so let's see what happens. The answer is, maybe let's think about what the answer is before we actually look at the results. Now, probably you already saw this. I suppose I could edit out the video, but whatever. The answer is we are not going to get exactly the same thing. And that is because the definition of the SVD, or the way to obtain the SVD, is by the eigendecomposition of the matrix times its transpose, and then the matrix transpose times the original matrix. Now that is, you don't use the matrix plus its transpose because, in fact, in the general case, that won't even work. This is one of the manifestations, one of the examples that I just mentioned when I was showing the book chapter, that although these two kinds of matrices share some properties, there's many other properties that they do not have in common, including that A plus A transpose is not guaranteed to be a positive semi-definite matrix. And that you see here. The eigenvalues can be negative for this matrix. Okay, and then we see that, in fact, all of these relationships that exist for A transpose A basically break down because, A transpose times A is quite different from A transpose plus A. So the singular vectors are not guaranteed to be the same, and those are not guaranteed to be the same as the eigenvectors. Okay, so what is the grand overall conclusion of this exercise? I suppose it's that the relationship between eigendecomposition and SVD for square symmetric matrices is true only for matrices that are created as A times A transpose or A transpose times A.